Okay, hello everyone. Welcome to my channel again. So today I would like to talk about the Leetcode315 problem. Count of smaller sums after self. Okay. Okay, I think I make a wrong topic. Okay, so we will go to the problem description at first. You are given an integer array numbers and you have to return a new count array. The country array has the property where count I is the number of smaller elements to the right of nums I. So we need to be clear that we understand the description of the problem first. So I will take the example like this one. This one. Why it has the same? Okay, I think I will refresh it. Oh, well, okay. Wait a second. I will open a new one. It might be this one. Okay. So here first we will see that I will take the example of problems. The example problem is 5261 and we should output 2110. Why? Because you want to find the count of the smaller number at the right side. So take the first one, 5 for example. If 5 at his right side, the number smaller than 5 is 2 and 1. So we need to return 2. And at the right side of 2, there is only 1 is smaller than him. So it is 1. Here, almost 1 is smaller than 6. So here is also 1. But on the right side of 1, there is no any 1 can be compared with it. So it returns 0. So here we can deduce that the last element must return 0. Okay, so I think everyone must figure out, understand what does this problem want us to do. Okay, so uh, my my solution to this problem is use binary search tree. I see someone will use the vector and lower bound to uh, maintain to get the answer. It is a good thinking, but I think it will cost to big O n square. That would not be a good time complexity. So I would like to use binary search tree that can even help us to give uh, each time search will only cost big O log n, and for after inserting all the tree nodes will get end with big O n log n. That would be very better than big O n square. So okay, so first we need to think about order of input. So okay, if we just take input for example, if we get input from left side to right side, if 5 want to get the answer for him, he will need to in, insert all the tree node to make sure how much number is smaller than him. Of course, if one want to get the answer who the number of who smaller than him, he also need to insert all the number. Okay. However, if we try to get number from right side to left side, what will happen? Uh, if we insert 2 first, we already sure that will be 0 because there is no one on his right side. And next we get 6. 6 just need to check one number because there is only one number exist at his right side, which is 2 and is smaller than him. And if we insert 1, uh, that is also already two tree node in our binary search tree, and we just only need to check them. So in fact, with this order of input from right hand side to left hand side, we can get our insert time complexity only need to be on. Okay, so this is the problem about order of input. So second is definition of our node. Okay. So I think the second one is very related to the third one. The two conditions we need to consider about. So I will directly go into the ideas of our binary search tree to let you know why I will define my node like that. Okay, so first, this is the tree root node, and we already know that we input from right hand side to left hand side. So which means that each time we need to find the smaller one, and that means if we insert a new node, we need to check how many smaller number in our tree. Okay, this is important because if you don't know what we want to do is this thing, then you will get wrong and don't know how to define node and don't know what we want to get from this binary search tree. Okay, so this is root node, which means that the first node we will insert into our tree. So this means that this is the last element. Okay, so Next node we want to insert is the last two element. So when we insert, I assume that I will take this example 5261 5261. So the number one is 1. And because this is binary search tree, next one I insert a number bigger than 1 and I would need to insert on the right hand side. And next one, because I insert a number bigger than 1, so it should be on the right hand side of 1, but be the left hand side of 2. Okay. And 5, because it is also bigger than 1, so it is be right hand side, and also smaller than 6, so be the left hand side of 2, and be the right hand side of 2. Okay, so this is how our binary search tree uh, I can say that this is a variant of binary searches that is not so balanced. Okay, but this design of binary search really help us because you can find that is with the tree level goes down and the ID of numbers will also go down, which means that we can only uh, search down to find the element we want because he can only be on our left side. We need to search down, but we cannot search back. Okay. So next, what is two kind of definition? Two kind of condition we need to consider about. So we want to find uh, a smaller number in existing node, right? So in other words, that means that the new node is bigger than existing node, right? So we need to check that when we insert a new node into it, whether it is bigger or not. Okay, so you can see that here, take this for example. When I insert 6 into the right hand side of 1, then I can say that okay, I uh, I have the count that I am bigger than 1, so the count is 1. So um, here also, if 2, okay, so on two side of the root, if A is bigger than S, if A is bigger than S node, then B is also bigger than S node, right? And C, because he is bigger than A, so in addition to the S node, he also need to add 1. Okay, so here A bigger than S node. If A bigger than S node, then B will also bigger than S node. And C will bigger than S plus 1 node. Okay. However, this one is only our root node, so his s will be 0. So because 6 is on his right hand side, he will become 0 plus 1 equal to 1. And here 2, because he is on the left hand side of 6, so it will still be 1. Why? Because he is still bigger than 1. And here, because he is on the right hand side of 2, so he still need to plus 1. Okay, so we get the number. So you think this already finished this problem, right? No, you are wrong, because there is still another condition. We assume that when we try to insert the 6, however, there is already some node on the left hand side before we insert 6 into the right hand side of 1. Then in this condition, we might need to write in addition to plus 1, it should also add the number of left children on this side, which is 3, so it should become 4. So we could not only use this to judge that how many of the smaller numbers. So here in my node, I also define another member which is called less s, which means that which will store the number of the nodes which is smaller than him. So s is himself smaller than on the right hand side, how much number is smaller than him, and the ls is on the other side, how much nodes will smaller than him. Okay, so each time when a new node add into the root of left hand side, the root less s will plus by 1. Okay, so this is the rule of root ls, and the right hand side plus 1, left hand side stay still is the rule of s. Rule of s. Rule of ls. So what is our final answer of count? So count would be root ls plus root s. And if it is on the right hand side, you would need to plus 1. If the node is on the left hand side, you don't need to plus 1. So this is my idea of the solution of binary search tree. So let's come to see the code. Okay, so this is my code. So So first I create a global number which is our final result called count. Okay. So each time I will update the count when I mm, add a new node. So here first we need to create a root node for the tree. Then we can use recursion to add a new node. And here we can see the reverse order of input. And please remember you don't need to use reverse first because it will take on. We just need to input from the back to the begin. That would be okay. Okay, so when we go to update, okay, let us see our definition of node first. So here is the important point S and ls, and here is left node and right node, which I will initiate as null pointer. And in fact, this is different from this is smart pointer, so you need to make sure that its method of use is different from the traditional node. And the advantage of using smart pointer is that it will destruct itself after the scope of function. So we don't need to control new and delete by ourselves to make it release from the memory. Okay, we will go to the add function. Okay, so first we can separate this to two parts. First part, the first two if condition is used to find place to insert new node. And when I find the right place to insert, we will come to here to insert new node. So why? How do I judge that the place is right for me to insert a new node? Because you can see here, if the value is bigger than root value, you would like to insert at the root right side. However, right side is not a null pointer. I will take this for example. So if you want to insert 5, so you will go to the right side of 1. However, you already find here is 3. So you will need to make root become here by recursion and try to insert to the right hand side of 3 again. Now here is null pointer, so I can insert 5 at here. So this is how the whole two part works to find the right place to insert our nodes. Okay, so here is find the right hand side, here is find the left hand side, and the second part is insert action. Okay, so here, here, and here, 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 here would be the most important point we need to care about. Okay, so first if I insert into 3 the new node bigger than root node. So okay, so I will talk about this later. And if we insert a new node which is bigger than root node, then just like I just say that 1 ls, the node on his left hand side need to be bigger, need to plus by 1. Okay. So now if we insert it, I already say that right hand side will s plus 1 and left hand side will stay still. Okay, so here I also say about it. Okay, so I will give an example such like 5. First, he will if 5 as our root node, s will be 0, ls will be 0, and c is counter, c will also be 0. Then we insert 1. So 1 here, ls will become 1 because 1 is on his left side. And mm, so what is the member of, how about 1? It will get s also initial to 0 and ls also initial to 0 and c also 0. Next, we will insert 6. And so 6 is different. If we insert 6 and is s will be 0 plus 1 plus this one will be 1. However, here we initial ls as 0 and our count should be 1, right? But we all know that is wrong because in fact if we input 5 1 and there are two numbers smaller than 6, so counter should be 2, right? So what is wrong? uh so that is what I do in here. On the path to you add the new node, you will need to add the you will need to add the yes, right, you will need to add the ls on the path. So here, for example, here is a, here is b, and I find that he is bigger than 3 nodes, and at here is b. B find that he is bigger than 4 nodes. And then we come to c. So c he is bigger than these two, right? And in addition, he is also bigger than this 7 node. So on the path to insert our new node, we will also need to add the nodes on the path layer ls. So besides s, we need to add 3 and plus 4, it will become 9. So here is also like that. On the path, we will also add OLS, just like this one. So it will also add 1 and become 2. Okay, so this is the idea of this problem. Hmm. It is a shame that I use so many time to debug and create the structure of this tree. Okay, so I think the time complexity is O n log n. It would be greater than n squared. Okay, so if you find any wrong and any problem from my video, welcome to challenge me. Then my code will be put onto the GitHub, uh, and also I will give this link in my video description. Hope you can learn from my video or help you solve the problem. Good night.